Okay, welcome back to the second talk. I'm very pleased to be able to introduce Mike Wolf, who's going to talk to us about ray structures on Teichmuller space.
Thank you, John. So thanks very much to the organizers for putting together this really wonderful conference in this wonderful place where I get to see my old wonderful friends. I'll stop there and maybe make some new ones. Okay, so I want to talk about ray structures in Teichmuller space. So what do I mean by that? So Teichmuller space is a cell. Okay, so here's Teichmuller space, it's a cell. And what I mean by a ray structure is for every point you take in Teichmuller space Z, I'm imagining you have a sort of foliation of Teichmuller space by some notion of rays where you just define what they are. Okay, so from every point I sort of can look out in unique directions and fill out the space. Okay, so and there's a number of these that exist already, and I sort of want to talk about how they relate to each other. All right, so let's see. So as usual, so S is a surface, some differentiable surface of genus G, at least 2, oriented, on which I'll put various structures. Okay, and so the talk, like most talks so far, sort of unfolds in layers. So I will try to talk for a little while about the setting, then I will get to a rough version of the statement, then I'll get to a more precise version of the statement, then I'll do some elements of the argument, and then I'll try to stitch things together and maybe do some applications. So what is Teichmuller space? In the second week of this program, probably we should, I think this is known, but I want to highlight sort of a point of view. So there's conformal structures on the surface up to the usual equivalence, or classically, it's hyperbolic structures on S up to pullback by diffeomorphisms near the identity. And the equivalence between these is the famous Kerbe uniformization theorem. Maybe Poincare is in here somewhere. Maybe I'll put Poincare in here, both around 1907. And so, and in some sense, I'll be provocative at the beginning. I mean, the story of Teichmuller theory is understanding how to get back and forth between these two perspectives. So, you have something defined conformally, how do we understand it hyperbolically? You have something defined hyperbolically, how do we understand it conformally? How does this sort of transcendental uniformization actually work in practice or in examples? Okay, so, and of course there's other definitions that I won't get into. I mean, Sarah was talking about discrete faithful representations of the fundamental group of the surface into PSL2R. So maybe I will say that one because it gets us a little further. So discrete faithful representations of pi1 of the surface into PSL2R. And then these are then related in the Hitchin theory to quadratic differentials, and I'll sort of use the Hitchin notation here for using so this is the theory of Hitchin, and in some sense harmonic maps, and I had some involvement with this as well. Okay, so we have a variety of ways of looking at these things, but my goal overall, just sort of said schematically, here's my mental picture, is that on the conformal side of things, we could think about ray structures, so-called, Teichmuller rays. So we have Teichmuller I don't know if this has actually been developed in the past couple of weeks, but it's classical. We have Teichmuller maps, Teichmuller differentials, and from a Teichmuller differential, one has Teichmuller rays. I'll say more about that in a moment, just in case it hasn't been discussed. And then on the hyperbolic side, something that's gotten a little more discussion. It's not so much talked about. It's a bit of a stretch to call these rays, but we have this sort of Thurston metric geodesics. It's just sort of a way to get between hyperbolic structures. So here, Teichmuller rays get us between conformal structures, hyperbolic rays, Thurston metric geodesics get between hyperbolic structures. And what I want to try to argue is that these are two endpoints of a continuum, and what mediates or interpolates between these two perspectives are harmonic map rays. So that's the theme I'm going to develop. And of course, I have to now define what everything is, but just so you have some idea where I'm going to, I'll say as a few more words, Teichmuller rays, as I hype and, so we'll be left with hype over here and conformal over here. That's the rough picture to develop. Okay, so, great. Okay, left out some things. So, so all of these refer to variational problems. And so variational problems on surfaces. And in some sense, they're reflections in Teichmuller theory. So that's the next passage in this discussion, is to think in terms of these three types of rays, what are the underlying variational problems, and to describe some of their features so that they'll be around for this basic theorem. Okay, so on the conformal side, so first I'll do conformal, then I'll do hyperbolic, then I'll do harmonic. So very quick tour of Teichmuller maps. So, we're given some surface X, or some pair of surfaces X and Y in the Teichmuller space. If you like X, I can write this as the surface with some almost complex structure, Y as the surface with some other almost complex structure. And so in Teichmuller, so over on Teichmuller space, I have X here, I have Y there, and I'm interested in how to get between them. And so I look at maps F from X to Y, and I ask, if I look at the quasiconformal stretch of F from X to Y, and maybe I'll call that K of F. And then I ask to look at the infimum of this over all maps that take me from X to Y. That gives me some number of K of XY, which describes the smallest quasiconformal stretch. Okay, so you can just write down this quantity, try to minimize it. And the remarkable theorem of Teichmuller, which gave rise to all of our paychecks, is that you look at a quadratic differential on the surface. Sometimes, maybe in this audience, I can just say the quadratic differentials. And so, so this is some tensor space. If you like, it's over here in X. I'm sort of trying to draw something sort of infinitesimal, or a tensor space over X, a cotangent space, or just a space of quadratic differentials at this point. You take one of these Qs, and so locally, now we've moved from Teichmuller space back down to the surface. Q in a local coordinate can be written as Q of z dz squared. And I can change away from the zeros of this quadratic differential. So how do I think of Q? I have the surface, and it's a holomorphic object. So first I look at the divisor of Q, where it's 0, and the Q has two different types of behavior. There's behaviors near the divisor, and there's behaviors away from the divisor, and that's sort of the dichotomy in thinking about this. But I can change coordinates to a new coordinate zeta by taking the square root. Square root is locally a 1 form. I integrate it, I get a new coordinate zeta, and in that new coordinate, d zeta squared is Q. And this gives, and why do I do this? Because now I have a canonical coordinate on this surface. And so in that coordinate, so I can look at the zeta plane, and the zeta plane has, is a psi axis and an eta axis. And there's two then, and the important part of this is that there are two distinguished sets of lines. There's the horizontal lines, which I'll draw in blue, and the vertical lines, which I'll draw in orange. And they may even be visible to the back row. Okay? And so back in this where I have a patch, these foliations on the zeta plane will pull back and give some sort of foliation in the patches on the surface. These will fit together at the singularities at the zeros in sort of a singular way, and we'll see pictures like this, which is presumably somewhat familiar to folks. Okay, these leaves that, of course, wind around the surface and come back in interesting ways, right? So that's the analytic side with Q of z dz squared, the picture side with the foliations, and what is the Teichmuller map? So Teichmuller, so the solution to what is the least stretch, which map has the least quasi-conformal stretch from x to y? The answer is there is some quadratic differential, Q, and for Q, you can look at the map, let's say FQ, and in these coordinates, it will take psi to k psi and eta to just plain old eta. So it'll just stretch in the horizontal direction. So this is a real model of what of how to think about. It's a model for applying a variational formula to understand the space. In that, I present a variational problem, minimize some quantity, and I tell you how to minimize the quantity. And this is all from any pair of surfaces x and y. But when you put the whole thing together in a single picture of lifting to the moduli space, to the deformation space, a Teichmuller space, I'll have this space of tensors at x, and in that space of tensors, we have, it being a vector space, we have rays, and these rays, via this plan of taking a particular quadratic differential, so maybe I have a ray Q, some particular Q, and I multiply it by t time, and I get a ray's worth of quadratic differentials, and that will give me then a ray's worth of deformations like this, which then describe a curve's worth of points in Teichmuller space, which all of whom are related by having the same basic stretch pattern on the surface, but just different amounts that that stretch pattern has been stretched. And it has and the Teichmuller's theorem is that this works, so that in the sense that you give me any pair, you take any base point, you can reach any other point uniquely with a ray. And that ray relates to the geometry in terms of being describing a solution to the variational problem of finding the least quasi-conformal stretch. Okay? Okay, now done with Teichmuller theory. So actually it's quite a joy here to be able to give a talk on old-timey Teichmuller theory. So that was the conformal side. We've had discussions in the past couple of days I've been here, and I understand last week, about the hyperbolic side. And so this is, if you like, Lipschitz, best Lipschitz maps. Maybe we could call it the Thurston metric. So various ways of of creating a rubric for this discussion. And so this has been done already, briefly. So I will continue this style of I will do it too briefly to distract. So here these are hyperbolic metrics. So maybe I'll say they have some, metric, emphasize symmetric gx or symmetric gy. And I look at how much this map, what's the amount of stretch that's required to get from x to y. I compute that as a function of the map, and then I take the infimum over all such maps, and I'm left with some number, L, which just depends on x and y, and I try to understand this in terms of which maps best, which maps achieve this infimum, if possible, and then how should I understand those maps in terms of the Teichmuller space? And so the answer, so Thurston's answer is that you can, that there is an answer to this in terms of what are the best maps. And in fact, this is Thurston, 1986. Teichmuller, probably like 43, though if the believable proof bears 60. So this gets related, this is parenthetical, I do need this a little bit, is that another hyperbolic problem you could try to resolve is to try to look at the supremum of, you look at you take a curve, alpha, and you look at its length in y, you look at its length in x, and then you say, well, what, if I look at the at alpha, a simple closed curve on S, how much do I have to stretch to get from x to y over all curves, and then take the supremum over this? And that'd be another way of comparing hyperbolic geometry. And the theorem of Thurston is that the Lipschitz constant that you get, which extremizes, agrees with the stretches that are required to get you from one curve to another. Okay, or the amount that lengths are deformed. Okay. Oh, I left out something. I'll come back. Okay. Sorry? I was emphasizing these are hyperbolic. And over here, I was emphasizing that they're complex structures. So I should emphasize again, it's a metric, but I've gotten sloppy. Oh, because I used a J, which is like the almost complex structure. But if you like, I mean, they're all integrable, so it's the complex structure, but the J was the tensor. Sorry? You didn't have some deep reason. No, I was trying to avoid questions from the audience. So, all right, let's see. Okay. And so the solutions, so Thurston provides something of a solution, which we've seen described already. There's some, if we look at, so I'm going to imagine in the background, I have a hyperbolic ideal triangle. And so this hyperbolic ideal triangle can fit into the hyperbolic surface. And as it has really long tails, right? So it will start wrapping around and get in somewhat chaotic ways, and produce on the surface. If I have back up. I want to recall that we have this notion of measured geodesic laminations, and I'm trying to draw a measured geodesic lamination on here whose complementary regions are all ideal triangles, which we've seen a few times. Okay. In that case, so this is supposed to be a cartoon of a maximal measured geodesic lamination. And what Thurston says to do if you want to achieve an extremal Lipschitz map is he says, a way to do that is to take an ideal triangle, as we've seen, look at the sort of horocyclic foliation on this, and then stretch this foliation by like e to the t. Then that will take this hyperbolic ideal triangle to itself, push it back onto the surface, and then a miracle happens that when you push this map back onto the surface, all of these ideal triangle, these stretches that you've done on each ideal triangle, maybe I should draw it in a different color, then match up, even though they're going to come through with like Cantor set intersections in all different ways. You can integrate the family of hyperbolic structures on each of these pieces in a way that that you create an actual, complete, well-defined hyperbolic structure that's new and that has been stretched by this e to the t amount on every one of the ideal triangles. Just amazing. So that's a Thurston map. So let me come back to the Teichmuller theory. Let's see. Okay. So over here on the Teichmuller side, I drew these rays. These rays are geodesics in the so-called Teichmuller metric, where the distance in the Teichmuller metric from x to y is 1/2 log k from x to y. Now I can create a Thurston metric, and in the Thurston metric, the distance is going to be 1/2, so again between x and y, we 1/2 log L of xy. Now in the Teichmuller metric, we were in a good situation because these rays are actually geodesics in this metric. These are more difficult in the Thurston metric, so in the Teichmuller metric, there's geodesics. In the Thurston metric, we could be in a good situation. Now, a basic invariant that's interesting is the, maybe I won't get too far into the details here, but sort of the optimal or maximal stretch lamination from X to Y. So this is the a lamination on the surface that contains all laminations that must, I think I want to say this properly. When I look to minimize, to look at the supremum of this, to look at the supremum of these two lengths, some laminations achieve that supremum. I can look at the union of all the ones that achieve the supremum, and they fit together to be a chain recurrent lamination. I'm gonna probably drop the words chain recurrent through the talk because I don't want to get too far into it. So there is, but one can look at which laminations get stretched the most, put them all together and call that capital lambda of xy, the optimal maximal stretch lamination from X to Y. Okay? Sometimes the optimal maximal stretch lamination is, the new use of the word maximal, a maximal lamination in the sense of having complementary regions that are just ideal triangles. Sometimes you win. I'm sorry? But not always. In fact, in some sense, rarely. But sometimes you win. And when you win, then this Thurston, well, I'm sorry. You can, sometimes you win. And when you win, then the Thurston stretch map will be a geodesic from X to Y. Okay? Moreover, you can always just impose a maximal stretch lamination, something whose complementary regions are ideal triangles, stretch along that, and that will be a geodesic. Now, yes, theorem. It's a chain recurrent, yes. So, right. I'll say the same thing a couple of times because maybe sometimes it takes a while to sink in. Now if I take one of these maximal laminations, I can stretch in that direction and I will have something that is a Thurston geodesic. This will allow me, if I want to get, so I'm stuck, I'll draw it again. So I want to get from W to Z, that's somehow a different picture. Now, I proceed along a maximal lamination by stretching these ideal triangles for a while, that's a geodesic. And I can actually achieve a minimizing distance from W to Z by concatenating these Thurston constructions. Okay? And so this is by stretching in one direction and stretching in another direction, I can get between any pair of points. It is not unique. And so I promised to say things twice. Let me back up to the surface. I can look at this lambda from W to Z in this case. So, and it could be that lamination from W to Z is not maximal. It may not have, it may have complementary regions which are bigger than ideal triangles. In that case, if you want to get from W to Z, well, a way to do that is take one of these take this complementary region, which is not a collection of ideal triangles, and add in more leaves so that you have ideal triangles. Then do your stretching using these, and that will start to have you proceed from here to there. At some point, you've stretched too much. In some sense, this point and this point have gotten very far away. This has gotten a little too short relative to z, and at that point, what you'll have to do is use the opposite collection of ideal triangles to proceed from here to here. Of course, I made a choice, right? I could also have done, so here I did case A and then case B, but I could have also done B and then A. What I mean to dramatize to you is that there is multiple ways of doing Thurston geodesics from W to Z, and there is, so the Thurston metric does not have unique geodesics. And in fact, there is some envelope of geodesics that get you from W to Z. This is a much more complex setting than in the Teichmuller case. Okay? I'm talking about a set of all possible geodesics from W to Z, and that is what I will mean by the envelope from W to Z. It is a union. I'm not telling you how thick it is or anything like that. Okay? I will later describe this for you.
Is there a combinatorial upper bound on the complexity of these geodesics? Because
yes. I mean, look. Great. Okay. Let me make sure in every one of these settings, I have to tick off all the various features I want to talk about and not the ones I don't. Okay, one more thing about this metric is that this is an asymmetric metric. In other words, it's not necessarily true that the distance in the Thurston metric from x to y equals the distance in the Thurston metric from y to x. Okay. Y, if you stretch in one direction a certain amount, why if you had a certain Lipschitz amount to get from x to y, would you need the same amount to get back? Especially in the setting where your metric isn't flat. Yep. Yep. W comes before Z by design. Harmonic maps. Harmonic maps are strange in this setting. So here I'm going to be looking at maps from the surface with a complex structure to a target with a hyperbolic structure. Okay. And so the quantity that we are focused on is the energy. So these minimize the energy of maps from, this is x, from x to y, given by, take the derivative of f, square it, and then integrate it with respect to the volume. Well, I'll put briefly a conformal metric on here, the volume of sigma. Now, I'm taking a norm here with respect to this metric as well. And when you check, if you multiply the volume by 7, if you multiply the metric by 7, the volume moves up by 49, but the size of the norm on the domain goes down by 49, and these cancel. So the metric doesn't matter, it's only the underlying conformal structure that matters. That was probably too fast, but I promise you it'll work if you just go off and think about it. So we minimize this. And I used here dimension 2 to do this cancellation. So it's in dimension 2 that we're mapping conformal to harmonic. And also, these also have rays. So this problem also admits rays. And the way this works is that you minimize, so let f from x to y be a minimum. And as George says yesterday, there's a conservation law which says, so this satisfies some PDE, there's a conservation law, and what the conservation law says is that there's a particular quadratic differential, which you can write in a number of ways. If you like, you pull back this metric, pull back the metric, and then use the complex structure to decompose it, look at its 2-0 part in the pullback, and that turns out to be holomorphic. So this is a quadratic differential back on X. Okay. So that's, and so it's, well, I say it's a conservation law. Holomorphic means it's debarred, one derivative is 0, and the Euler-Lagrange equation for this is second order. So, but anyway, so you get this quadratic differential. Now, and it's so now I should tell you a few things about this quadratic differential. Of course, you know, I made a big deal over here about saying that there was a picture associated to a quadratic differential, and the picture has something to do with the geometry of the map that induced it. Right? These gave the stretch directions of the Teichmuller map. So what about the picture here? What do the again, you know, you'll have zeros of this thing, and again, you'll have foliation directions of the quadratic differential, this so-called Hop differential. So I have these leaves back here on X, and what do they mean? And you know, once again, of course, we have singular points. And so the meaning here is that these horizontal leaves, these are exactly the directions of the maximal stretch of this energy minimizing harmonic map F, and the vertical leaves are the directions of minimal stretch. So if you have a map, you look at its differential, the differential has eigendirections, and the maximally stretched eigendirection is blue, is horizontal. It's the horizontal leaves of this holomorphic object associated to the harmonic map. And in this, okay, so in this case again, we have the same sort of schematic picture that we had in the Teichmuller case, in that if I look at Teichmuller space, and I look at X, then on X, I have this family of tensors, these quadratic differentials, and again, they have rays, because it's a vector space, so TQ, and it turns out, and this is a theorem, that, what color I used, that one can find points, say YT in Teichmuller space, whose, with this property, that along this orange curve, all of these YTs have the energy minimizing map from X to YT has Hop differential, this conserved quantity that is TQ. So all of the patterns of stretch of the harmonic maps are identical to this whole family of surfaces, of hyperbolic surfaces in Teichmuller space. And so these also, and it's a theorem, Hitchin and me a very, very long time ago, that these things foliate the surface, and we have the same sort of ray structure. So for any given x on Teichmuller space, you look at the quadratic differentials, you scale them, you look at the resulting surfaces whose harmonic maps have that quadratic differential, have that underlying quadratic differential projectively, and they fill out Teichmuller space. Okay? So now I have 3 ray structures. Okay, started at 11:30, I go to 12:45. Okay. Right. So let's warm up. You know Teichmuller maps, right? In the Teichmuller maps, the horizontal leaves are the directions of the Teichmuller map's maximal stretch. For harmonic maps, you look at the harmonic map. It's going to have directions that are the directions of maximal stretch, directions of minimal stretch. Those directions integrate to give you singular foliations, and those singular foliations are exactly the horizontal and vertical stretch foliations of the Hopf differential. Okay, yeah? I'm sorry? Okay, that's Thurston. I got quasiconformal stretch, I got hyperbolic stretch, Lipschitz stretch, I have harmonic map stretch. Yes?
Sorry, just to confirm my picture, the images of these 2 foliations under harmonic maps, when looking at them in Y, no longer gives us the correct complex structure for Y. Is that what's happening?
It gives the correct hyperbolic structure. So, you have X over here, you have Y over here, I have these horizontal lines, and then they get stretched to something longer over in Y. Okay. I don't hear well, sorry.
In the second case, do the stretch lines foliate?
Oh, in the Thurston metric? Sorry?
Yeah.
No, because you have this complicated picture of geodesics. Okay. Right. I mean, it's just complicated because, if you just have a maximal, if your capital lambda was maximal in the sense of having complementary regions that were all ideal triangles, then your envelope would just be a single line. Yes. Yes. Okay. Okay. Great. I got these 3 pictures. Right. And I'll remind you, so now maybe I'll remind you, the overall picture I want to present is Teichmuller rays on the left, Thurston metric geodesics on the right, harmonic map rays in between. And I promise to get to that in a month. Yes.
You told us about the ideal quadrilateral of polygons. What if you have 2 disjoint simple closed geodesics in your maximal level? That's possible, right?
Sure. Then your envelope is going to be much more complicated, right? Because you have all the different ways of decomposing the subsurface. Okay. Okay. So I mentioned that I did this theorem about the foliations a very, very long time ago. And it is actually, the talk is theological in the sense that this has always bugged me. Like, how does this picture fit into the larger Teichmuller theory? Okay. And so let me state the theorem of the day, or theorem of the talk. I'm going to get rid of this. So first I'm going to state it. Well, probably this is about as precise as I'll get. And I'm going to reference, so I've told you about Teichmuller rays, Thurston geodesics, harmonic map rays. I'm going to reference a fourth ray that is very obscure in that we just made it up. And, but I'll explain that later. Let me see if I can get to something. So there's two parts to the theorem, because remember, so I want to talk about, limits going this way of harmonic maps and limits going that way. So I have two theorems. First, fix your target y. Let xn, the base, the domain, let this degenerate along harmonic map dual rays, which I have to explain. There's a natural dual ray to a harmonic map ray. Then the harmonic map rays from xn through y converge to Thurston geodesics, Thurston metric geodesics. I'll draw a picture in a minute. Let me get the second statement up. Fix a domain, x. And this then let the target go to infinity, yn, along harmonic map rays. Then these dual harmonic map rays converge to through x converge to Teichmuller arrays. Okay. Those are the statements. At the risk of being didactic, let me just restate them with pictures. So for the first one, I have some good ways of going to infinity. That's the dual map. Forget that for a minute. I have a target y, and I have some family xn that's degenerating in a controlled way. Well, for each of these xn's, I think I used orange. I have a harmonic map ray that goes through y. That one goes through y, that goes through y, that goes through y. And my statement is that if you take a limit of that family, ... what you get is some arc through y, and that this arc is a Thurston geodesic. So we start with these harmonic map arrays that depend on the domain and the range. We wash out the dependence on the domain. The domain has a conformal dependence. We wash it out, and looking and in focusing just on that one fixed target, we see these rays converge to something which is entirely hyperbolic in nature. So Thurston geodesic. Okay. So that's the picture of theorem A. Mahan, what is your question? Yes. Now, so, okay, I owe you something for that. All right, so getting a little ahead of myself, but what you see here is that by adding, there's a few things to notice. The theorem has some strength to it, I should advertise. The first is, I said converge. I did not say subconverge. By using this family, I get actual convergence. Okay? That adds 40 pages to the paper. But what gets picked out then, if you do things properly, is a unique geodesic through Y. So in some sense, by adding in an ingredient that you want a Thurston geodesic, which is the limit of some other family that comes from energy minimization. So you add in this extra constraint, you pick out something unique. And so that I will assert later is useful. The sort of uniqueness that gets achieved this way in the Thurston metrics setting. No, this is real analytic convergence. Okay, so that's this setting. And then, there's of course, now I have you can almost draw the same picture over here. I have X, I have YN, I have these dual rays from X to YN, and that these will converge to a Teichmuller geodesic. And so this is I left out some words, but this is pretty close to the statement of the theorem, and that's the justification for this mental model that I started with. Okay, so these are going to interpolate between the two. Yeah, so the idea here is that there aren't real good, to my understanding of the literature, there's some discussion, there's some plans out there, Athanase had some, I think, among others, for what do you do in this case? What's a really good map? And this is our response. Okay, so because Thurston is silent on this. Okay, well, other than, cut it this way, then cut it that way. Okay. 20 minutes. Oh, I bet, okay. 20 minutes minus epsilon, yeah.
What if you did everything at one place? In other words, X is Y, put the thing around, then you have Thurston geodesic.
Yeah, but then everything's going to go to infinity together. I really want to fix, so, if you're, I don't know a good metaphor, you're,
I'm not sure if I said it right. I'm comparing the two geodesics. You have the Thurston geodesic at Y, you have the Teichmuller geodesic at X. I want X and Y to be the same.
Yeah, but I'm not going to let you do that because what the theorem, I mean, you can go to any of these, you know, more or less free countries, so, you know, this is. But the, I think I'm going to stop there. It's one of these things like, I don't know, like one of these physical tests, right? Focus your attention on Y. And while you're doing that, I'm going to let something, other piece of data drift away. But your attention's on Y, so you're just seeing the arcs through Y. And those arcs limit. But I have to fix Y in order to say that. But if I let, you know, but I'm still not going to let you do that, you know, because if you make X and Y the same point, I'm letting it both, the construction I'm discussing is when one of them goes to infinity. So if they're equal, they're both going to infinity, and then I don't know what you have. Okay, let me say what these dual rays are. Leave that up. I'm going to pretend I don't hear murmurings. Okay. So dual rays. Just I like to think of harmonic maps through an auxiliary construction. So harmonic maps from surfaces as minimal maps, minimal surfaces. This is with respect, so maybe I'll say area minimal surfaces in a singular three-manifold. And here's what I mean. We drew this picture of, I'm going to look at the lift of Q on the universal cover S. So, you know, we have some singular there's some zeros. You know, a leaf pattern, it looks like that. Okay. Map to the leaf space. So the leaf space, so now I look at the leaf space. And the leaf space is 1 point for each leaf. So in this case, we can sort of figure out what it is. Good color. Ooh, that's one I haven't used. So, you know, at this point I have 3 leaves, 3 branches. So I have, you know, that's a leaf. Anyway, you can see this is the leaf space, looks like this. Right, by drawing that yellow thing, I touch every leaf once. So I think of this as so I get some tree like that. And this is the tree associated to that quadratic differential. And this is a metric tree. So this foliation that I drew is a measured foliation in the sense that, well, it's a measured foliation. And so maybe you've met these, that you can say what the intersection number of an arc across the foliation is, and that's independent, that's well-defined up to isotopy of the arc. So in particular, that measure, so I have some measure on Q, And that measure under this projection to the leaf space pushes down to a distance. That's well defined. So this real tree, so the quadratic differential here and its measured foliation, say horizontal measured foliation, pushes down to a tree. Locally, let's see what this looks like. So locally you have Z, and Z, or zeta, and zeta is psi plus I eta, and I'm drawing psi this way. So this is pushing down to eta. Okay. So that's what the map is locally in coordinates. I'll point out to you that taking the imaginary part of a harmonic, of a holomorphic coordinate, this is harmonic. Okay, this projection. So for one of these quadratic differentials, I have a harmonic, just given Q, there's this auxiliary harmonic map to the tree. So, and what I want to look at, so I want to say is that if I'm looking at a harmonic map from X to Y, it has associated to it this quadratic differential. And with that quadratic differential, I have another map that goes down to the quadratic differential from X to Y, this pi. And now I have a pair of harmonic maps. And it's a true fact that a map, a product, so a harmonic, sorry, if I have a harmonic map to a product where each factor is harmonic, that map to the product is also harmonic. Sum of squares in energy is the sum of squares. So you can minimize both separately. Okay, so this is harmonic. Now, what's its quadratic differential? I have done this very carefully. I have projected along the directions that are stretched maximally. So the stretch to the tree is exactly in the direction which was stretched minimally to Y. So I now have a little more stretch in the minimal direction than I used to. Okay. Miracle. Actually, the amount, by mapping to the tree, by mapping to this product, the amount of stretch is exactly the same in all directions. So this map is conformal in that it's in every direction, the stretch is the same amount, because I washed out some of the extra stretch. So what we found then is if I think about a map, if I have a base Y and I have this tree TQ, I have X sitting in here as a graph, and it is conformal and harmonic. And being conformal and harmonic is the same thing as being minimal. I know there's only 4 words in mathematics, but minimal in this case means area, minimal with respect to the area functional. Now, what is cool about that is a number of things. First of all, you get to, I now have a minimal surface in something 3-dimensional. Okay? The study of this goes back to Euler. So I can access, almost 300 years worth of theory. Okay? The other aspect is that the harmonic map was parametric, in the sense it depended on how you, it depends on the parameterization of itself from X to Y. So you say where coordinates here go to there, it depends on the coordinates. This is not parametric in the sense that it's a state, being minimal is a statement about the embedding. It's just how this thing sits in here. It doesn't matter what the map is. So I've now removed something technical. Okay, I promised you so now I promised you dual rays. Why go through all this?
So the fact that Y is a real tree, it's for the least, right?
The T is a real tree.
That T is a real tree. Right? It's for the least, define minimal maps and stuff like that.
Right. I used the tree to make this suspension or this graph minimal. I lied a little bit. There's a 2 floating around, but
it's really bad, right?
Sorry? Oh, yes, thank you. The tree is awful.
Really bad, yeah.
Thanks, I should say that. The tree is awful. It's a real tree. I drew a bit of it. But remember, the way these leaves work is it's very much like the lamination picture. You have, I have this singular leaf, and I shoot it off, and it wanders around the surface, and where it goes is its own business, and it just wanders, and probably it's going to come back close. There's sort of an Anosov property. So it's going to, it's sort of a hyperbolic system. So it'll come back close. So if you think about what this lift is, I drew it very poorly in that, yeah, sure, it looks like this here, but if I follow this up, it'll become very close to some other leaf. So this singular point here, there's another singular point very close to it, which also branches. I'm doing yellow. So, and that's true everywhere. So typically, the vertices are dense, and if they're not dense, they're going to be infinite valence. So it's a very furry tree. Thanks. Okay. So what's a dual ray? So what's a ray in this picture? So I have Y, I have this tree, and I have X. And so a harmonic map ray is this. Take the tree, scale it by T, make sure you keep X, and then you're forced to have a YT. So YT is a harmonic map ray. I'm always going to have this picture. I can drive this in some linear way. If I fix that, this has to change. Okay. The dual rays that I'm interested in is the same picture. I have the tree here, but now I'm going to fix Y. I'm still going to scale this, and so this has to change. You have a relationship between three parameters. If you change one and fix the other, the third changes. Okay? And so this is the dual ray. Okay? And these are the ones that will eventually become Teichmuller geodesics. And these are the ones that will eventually become Thurston geodesics, or approximate. Okay.
Is the dual ray not just looking at backwards orbits of these harmonic rays?
No. It's this. Okay. So, so a lot of the analysis that we'll do is going to come down to trying to understand minimal surfaces in this singular space. Okay? Well, I know, I mean, when it's not singular, there's all sorts of theory, but here I have to worry about the singular spaces. And in fact, so let's see, what can I sort of look ahead to? So, so what is going on? Like if I let xn go to infinity, xn is a conformal surface with a quadratic differential. So, so looking ahead, if I have this surface xn, and I'll repeat, so this is surface with a family of almost complex structures Jn, and this is going to infinity. So what does this go to? Well, it's in the conformal setting. So this is going to go to some noded surface, right? If you like some surface with punctures, and the QNs, well, these are going to go to something that is holomorphic on this punctured surface. So if you like, it'll be something, with luck, which is mirrormorphic. So we'll start having poles at these punctures that'll develop, and those, of course, they would, in some sense, we have to have something singular because as xn retreats in Teichmuller space, the energy to y is going to blow up. How do you think of this? You imagine what's the simplest way of going to infinity, as we've discussed, you could pinch, right? So, but if I pinch, then I have a very short curve here, and it's going to something of moderate size. So I have to have a lot of stretch. So I'd have to have a lot of stretch squared. Now you have to do a short computation to realize that the integral of this amount of stretch squared is going to be arbitrarily large as this gets smaller. So, so that blow up has to show up somewhere, and it shows up in these differentials being mirrormorphic. Okay. What else little bits can I fit in to get myself ready? Okay. Oh, okay. So last bit of the statement of the theorem. The theorems. Okay. So as Mahan, managed to get out of me, we have found, grudgingly, what got from me, we have found some unique or canonical, maybe I'll say it this way, canonical Thurston geodesics we have found for each pair XY in Teichmuller space, canonical Thurston geodesics from X to Y. Okay? Or maybe I should say, we will find. So I can find good harmonic maps from X to Y. I can take a limit and I'll find good canonical Thurston geodesics. So, so in other words, there's going to be, so we're sort of improving the envelope picture, because now from X to Y, I have some particular Thurston geodesic harmonic stretch line. Okay.
This is not a local species. The way you drew it there, you only drew it locally.
I know.
But it goes between X and Y.
I haven't, so I'll show you a construction on Thursday. It's very simple, where we'll find, I'll find rays, I'll find some Wn, which will connect these two, and I'll let Wn go to infinity, and it'll produce a line from X to Y. Yeah, all right. Yep, okay. We'll find for each pair YZ. Okay, I'll find something from here to here, and the way I'll do that is I'll find a good XN of harmonic map rays from XN that go through Y and Z, and then I'll let XN go to infinity, and I'll be left with just the segment. Okay? And now, so it's a cliffhanger. So the, I don't know if that's, okay, so I'm too old. You guys are, I'm too old. All right, cliffhangers like when TV shows were like once a week. Never mind, but I digress. audiences these days. Okay, so, but what we could also do, we can do the following as well. I can have y here and some point on the Thurston boundaries. This was always Teichmuller space, and now I'm going to look at the Thurston boundary of Teichmuller space. And the Thurston boundary, as I think has been described, is projective measured laminations. And so I have some projective measured lamination eta, and I can play that by letting z go to eta, I can play the same game. And the point is that we will end up with a ray structure. So this will lead to a ray structure on Teichmuller space for each y. So I'm going to foliate with unique limits on PML. So for each point on the each projective measured lamination, there will be a line that ends with limits on exactly that point. And so you'll have this sort of, I don't want to call it an exponential map because exponential maps refer to having infinitesimals and integrating, but you have the sort of the remnant picture that you would get from an exponential map with a visibility boundary of the PML. So that'll be the last outcome. So in the next talk, so we've now done the first quarter of today's lecture. So no, actually, it's gotten further than that. In the next talk, I'll do elements of the proof that have to do with what it looks like to have a very, very high energy harmonic map. That'll account for the stretch. And I spent a certain amount of time on the convergence, by which I mean not just subconvergence, but convergence. And that has to do at its core with these being minimal surfaces and certain uniqueness aspects of minimal surfaces that are useful, and a few other little tricks along the way. Thanks.
Great, thank you. Have we got some questions? Or I should say some more questions.
Oh, is the question, when do we get to go to lunch?
So this is resurrecting this question they were asking about. But if you allow both points to go to infinity, and you have a sequence converging to say something that starts off at one point on the boundary and goes to the other point. So from one point to
I see. You want to send xn to infinity and y to the other infinity.
Right. And in a controlled way, and you get Thurston geodesics from in one direction and Teichmuller geodesics in the other direction. Is that conceivable?
Probably. First of all, I hope you don't do it because then I have to referee the paper. I mean, really, you'd end up, I guess, looking at harmonic maps. I'm not sure. I mean, on the one, so here, if you go this way, you'll get a tree. And so you go this way, you're going to get this like noded surface with something meromorphic on it. But when it starts looking at these points really far off, even that meromorphic differential is going to blow up. So I can imagine what you would get I'm not sure.
Okay, maybe we can leave that question for late night discussions over some beer. But, okay, other questions? Okay, well, let's thank Mike again.